So my plan, and if I ever plan too far out, run me over with a car, please. But my plan for today, I'm going to do this review with you guys. This would be helpful for you for the quiz on Monday. Now, somebody during my fourth period business account class had a really good idea how to get me out of the normal training. And I need you guys to be involved in this too. They are going to kidnap me. Sound like a good plan? Whoever kidnaps me, I'll take you to breakfast.
I bet.
That gets me on a Monday. Gotcha?
How you want us to kidnap you?
Figure go get one of those weird white vans, pull up, throw me, put a hood over my head, throw me in, so people can watch. Make sure there's no plates on the vehicle. It'd be awesome.
And when we tell the police, we just get it.
Yeah, I got you. You know that. And I just have to go before the judge saying, look, it was a type 1 error. We were just to know when it was really true.
We were trying to take a stat.
So, so I'm going to go over this today. On Friday, I will then teach the very last unit of this, which is 612. Monday, you'll have a quiz on 611, or 6.8 to 611. It's already gone around? All right.
No, they have.
Oh, you guys.
Wait, we didn't get it either.
Oh, you get it? Okay. We'll make it work. All right. And then on Tuesday, I will then go over the assignment for 612, which I'm teaching tomorrow. And then we'll start the review for the unit on Tuesday. On Wednesday, we're going to do the second review. And then on Thursday, we're going to do the test for the whole unit. And on Friday, what comes Friday, other than the day before spring break? The orange story. Okay? Good. Someone listens. I like this. You guys, I think you like the orange story. It's pretty good. It's again, my friends. I truly think it's the Super Bowl of all the stories I've told. The ones that I'm allowed to tell as far as high school goes. Hey, I was waiting for you. Now I can start. All right. So this is page 117. Yes. Oh. Someone didn't get it over there. There we go. All right. So explain the circumstances under which you should perform a t-test instead of a z-test. Okay. So t-test versus z-test. Okay, things that you would have with the z-test. You would have the standard deviation of entire population. Whereas the t-test, you have the standard deviation of your sample. Okay, so right there, that's pretty much the number one spot that's going to take place. Okay, so if you're given the standard deviation and it's given as the entire population, z-test all day long. Okay, that's normal distribution, blah, 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 blah. Agree? T-test is that's not here, not here, not here, not here, not here, not here, not here. Oh, Jeremy, I found one of yours. It went past you. Not here. Oh, I knew I had one in there. There you go. All right. So, does that make sense for the first characteristic of C versus T? All right. Now, other things that take place. If one of the blues has taken place, that's going to direct you one way or the other. So if you have this as far as the z-test, and your sample is greater than 30 or the n times p is greater than 10, and the n 1 minus p is greater than 10, then that's going to work. If the sample is less than 30, or that n times p is less than 10, or n 1 minus p is less than 10. So that's basically the thing. So as you read a problem, if it says here's the standard deviation of the entire population, you should be thinking z-test. So then the next thing you're kind of scrolling to is my sample large enough? Is it about 30? Okay, so if sample standard deviation is given, sample is bigger than 30, you're going with z-test, normal distribution. Okay, or if I give you percents, 30% of people, blah, 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 and then you n times p is greater than 10, and 1 minus p is greater than 10, z-test. Okay, if I gave you the standard deviation of the entire population, and the sample is not bigger than 30, or the n times p is not greater than 10, and 1 minus p is not greater than 10, then you go back to the z-test. Okay, so, or the t-test. A t-test could indeed have a sample size of 10,000, and that still works. Okay, so remember the t-test, the t-distribution looks very similar to the normal distribution, especially the higher and higher and higher you get with the sample. Okay, so if you had a sample size of 100,000 and you did a t-test versus a z-test, you're very close. Okay, like honestly, if you use one versus the other, you might have a decimal that's different, like 8 or 9 decimals down the road. Okay, so no one would ever be able to find that out. Okay. All right. Explain why some statisticians argue that for a very large sample sizes, it's okay to use either a z or a t-test. Well, I just answered that. Okay. As your population gets bigger and bigger and bigger, the t-distribution looks like the normal distribution. Again, it's so very close. I mean, if you just wanted if you wanted to try and prove or disprove it, there we go. That's what I want you to do. So if I did a normal distribution, if I did that, and then I did a t-distribution where we were, if I did a t-distribution with like 1 billion people where my degrees of freedom is like this, okay? These two tests are so close to each other. Like even if you went and found some region way, way out far. So if I did this between -1, +1 on both, and if I did this a little bit bigger, and this, oh, come on, I want. And then I did this. Okay, so I want you to see something. So normal distributions on top, t-distributions on bottom. T-distribution, we have a sample size of 1 million, so our degrees of freedom is 999,999, which is like a really huge sample. So if you take a look at just the area within one standard deviation between the two, so 0.682689. There's a 4 here and there's a 2 here. So you are 1, 2, 3, 4, 5, 6, 7 decimals over before you start seeing a small difference. And again, in statistics, how many decimals do you really take things out? I mean, in here we usually go to 1, maybe 2 on occasion, 3 if like lightning struck 3 times the tree outside within 5 minutes. I mean, those two things are so close that there's doesn't become a big difference between the Z and the t-test. Okay, and that deals with a very large population because most of those, if I were to say, hey, what's the area within one standard deviation, I'd say 68.3 and 68.3. And you would never know there's a difference between the two. So that's the big thing there. So is there theoretically a difference between the two? Yes. A t-test is a t-distribution is approaching what the normal distribution graph looks like. Will it ever get there? Uh-oh. Another gift card? Oh, this is the best day ever. This is a birthday card for somebody. Cool. I got this due too. Whatever you did, blame me. I'm sorry, I threw it on the floor. All right. So we're good on 1 and 2. Everyone feel comfortable? Have we chased those dogs around the tree enough times? All right. Number 3 says, is the average ACT score of people who live in North Dakota greater than 21? I don't know. Is there even 21 people that live in North Dakota? It says a random sample of 75 North Dakotans shows an average ACT of 22.2 with a standard deviation of 6.2. Is there evidence at alpha being 0.10, so a p-value of 0.10, level to support this theory? Complete the hypothesis test below. Okay. So, random sample of 75. 75 a bigger number than 30? Yes. Sure is. So we're thinking it could be a Z distribution. But where is the holdup? Where's my holdup on number 3?
We don't have the standard deviation of the population of the sample.
Yeah, I have the standard deviation of our sample only. So we have to go right to a t-test. So let's clear these things out. I don't need these any longer. I think this was a pretty good demonstration. All right, so let's see who is listening. If I have a random sample of 75, my degrees of freedom would be
74.
74. There you go. All right, 74. I like this. All right. I don't need that right there. All right, so there is my random distribution. Okay. So, how are we going to proceed a little bit further in this problem? I don't know. Let's see. Let's do some stuff that we know. So this is problem number 3. All right. So we're going to say, here's our null. Here's our alternative. We're going to say ACT is equal to 21, and they're claiming the ACT is greater than 21. Hey, 1 or 2 tail? 1 tail, directional. They're saying, hey, they think it's greater than 21. Okay? And then we have our sample, our standard deviation. All right. So let's create our normal distribution or our t-distribution on this. So let's kind of draw that up here. And then this is going to be 21, because that's what our entire population was showing. All right, so I have to find the standard error. So the standard error is going to be what over what?
6.2 over the square root of 75.
Yeah, the standard deviation over the square root of the sample. Good. So 6.2 you said divided by the square root of 75. It comes out to 0.7. Oh, thank you for doing that for me. So we got 0.7. Okay, this is my standard error. All right, so we can do this. The screen line is going to be 21.7. This next line is going to be 22.4. And this is going to be 23.1. And then if I went the other way, over here, that's going to give me 20.3. And then that's going to give me 19 point, oh shoot, 6, thank you. And then 18 what? 18.9. Cool. All right. They said their average was 22.2. Excuse me. So 22.2 is like here. So visually, it looks like, well, it looks like it could be kind of far away from the mean of the whole thing. Excuse me. So now we have to figure out a couple other things. Let's figure out, it's the same thing as the z-score, but we're going to do the t-score. So it's basically our what? Our score minus our known over our standard error. All right, so my t-score is going to be this. So my score that, so like this is what is known. So they say we know at 21. Oh, wait, I went the wrong way. I'm sorry. I'm screwing things up. You can't take me anywhere these days. I'm going to go 22.2 minus the 21 divided by the standard error. Anyone get that? 0.7?
Or no. Yeah, I thought you meant the standard error.
22.2 minus 21 divided by standard error. Where did I screw? Oh, I'd be a much better teacher if I could actually do math. Okay, that divided by 0.7. So we're going to get a t-score of 1.7. All right, this is what now we can plug into Desmos to see if we can fail to reject. Remember, we're using an alpha of 0.10. Okay, it's a one tail, so we don't have to double it. If it was a two tail, we'd have to make it 0.20. So 1.7 standard deviations above the mean. So 1.7 to infinity. My friends were busting out with 0.047, so 0.05. So 0.047. So we found our t score. I don't know, I gotta go back and look at it. 0.047. All right. So little critical thinking, friends. Is that t-score of 0.047? Is it bigger or smaller than 0.10 or alpha? This is smaller. So this is smaller than alpha. So we reject. Okay. So the t, so what you have to do is you have to figure out this value. So this is like the z distribution. So your score minus your known. So like the entire score, which was that you knew is 22.2 from your sample, minus your known of 21 divided by the standard error. And if you do that, you get 1.7, which means you want to go 1.7 or more standard deviations beyond the mean. And that's what I'd have to plug into Desmos. Okay. So being that we came out with our t-score of being 0.047, and that is smaller than our alpha that we had set, which means we reject our null. Hi, Ruby. Good to see, buddy. So reject null. Now, something that I want to make sure you got. We found strong evidence against the null. Okay, so friends, when I use the word strong, that's kind of something that you lead people to be able, when they identify, they look at it saying, okay, strong evidence, that means there's really good evidence. If you just said I found evidence, so the thing is, by putting the word strong in there, you're indicating, hey, this is something that's taking place that you need to deal with. Hello. Yeah.
Could you run back over that?
Yeah. So my decimals and your decimals might look a little different. You might have the little box down here where you go 1.7 to infinity. For some reason they changed the computer. It's probably coming to the phones eventually.
And then the shaded region is from 22.2 onward.
So the shaded region is from 1.7 to infinity.
But isn't the
Yeah, so, I understand what you're saying. So yes, this is our
22.2?
22.2, but realize our x-axis is counting 0, 1, 2. So we had to like make this revolve around 0 to use the t-score, because it doesn't allow us to plug the mean and standard error in on a t-score. They ask for the degrees of freedom, so then you have to adjust it back to,
Oh, okay.
how far numerically would it be. So yeah.
Could I run up so much?
Cool. All right. Hey, we doing okay? Dang it, I forgot to take attendance.
Sir, please don't forget about me.
Oh, hey, do me a favor. Good. Hang on, can you take this Dean Weber's office today? He was not here.
Oh,
You know where Weber's office is, right? Go up the stairs. Right. Yeah, to the right.
Okay.
Just say he wasn't there.
Who? This kid?
That kid.
All right.
No best day ever. I cried myself to sleep for one of the days, but after that I got better. It happens. All right.
For today? No, I didn't. No?
We're just doing like the.
Oh, wait, then why do you not say anything?
Because I
Then I'm
got
gonna
beta.
Next time I'm pissing off. I didn't know if she was in beta or not. Sorry. It was like a 50-50 chance of texting you.
I saw your message, I couldn't text back.
I'm not skipping. I was,
All right. Hey, friends, do we feel comfortable with this problem?
What?
We're good?
I literally just
Turn the page. All right. On page 118. Says it is known that IQs are normally distributed with a mean, bless you, of 100 and a standard deviation of 15. Is the average IQ of people left-handed people higher than 100? Is the average IQ of people left-handed higher than 100? A psychological researcher selects random sample of 40 left-handed people and finds that the IQ is 104.2 of those lefties, and alpha set at 0.01. Ooh, we're setting alpha really low. Is there strong evidence to support this theory? Is this a Z or a T? Oh, this is a great problem. All right. So again, this would be really helpful for you on your quiz that you'll be doing on Monday. All right, so for problem number 4 on this page. All right, few things. IQs normally distributed with a mean of 100 and a standard deviation of 15. So friends, do we know the entire population standard deviation then? I do. So what are you thinking right away? Z-score, okay? So a few things. There, thank you so much.
Yeah.
So,
There, but I gave it
to the secretaries.
Yeah.
Perfect. All right. So being that we know that the mean is 100 and the standard deviation is 15, this is the entire population. So this means we're going to be able to do a normal distribution. Agree? All right. Now, they also said we did a sample of 40. We did a random sample of 40 people. So is 40 bigger than 30?
Yes.
Yes. So again, that supports that we could do a normal distribution. My friends, if that sample was like 25, that means we have to go back to the z-test then. Or the t-test, excuse me, the t-test. Okay? Does that make sense? Okay, so because that red sample is 40, 40 is a bigger number than 30, we can stay with the normal distribution, which is going to be a z-test. If that sample was smaller than 30, even though I knew the population standard deviation, it has to go to a t-test so we deal with the degrees of freedom. Friends, does that make sense how I said that? Cool. All right. So since this professor had done this test, they found the test had 104.2 IQ and finds an average IQ of 104. I don't have a standard deviation. They found us. Okay, we're okay. And then they want us to use alpha of 0.01. Okay. Hey, friends, this is pretty darn small. Agree? This basically means we are confident with our studies that we have a 1% chance of making a type 1 error where we rejected the null when it was really true. Okay? So they're pretty confident about their study. All right, so let's create our normal distribution. And then we know that this is a Z because we know the entire population and our sample is also bigger than 30. All right, so let's figure out our standard error. So our standard error is going to be our standard deviation divided by the square root of our sample. So our standard deviation is 15. Our sample is 40, so I'm going to go square root 40 and check to see what the calculator is going to do for us. So 2.4 roughly. That's my standard error. All right, so 102.4.
Is it one tell or two tell? One.
Oh, I didn't even create my null hypothesis yet. I'm being a dirty mathematician. 104.8. And then 107.2, I believe. Wait. 104.8 plus 2.4. 107.2. Hey, sweet, I did the arithmetic right. Then 100 minus 2.4. So that's going to give me the 97.6 minus 2.4. That's 95.2 minus 2.4. 92.8. All right. Sweet. And then things that we know because of this 104.2. 104.2 is like here. All right, so now the dirty mathematician is going to create our null and our alternative, even though I did math related to it. All right, so we are going to say IQ is equal to 100, and then we're going to say IQ is strong evidence. Okay, it is known that IQ is normally distributed mean standard deviation. The average IQ of left hand is higher, so is greater than 100. Okay? So we got that information. I think we're ready for our best buddy and pal in the Desmos family. What do y'all think? All right. So on this one, it's kind of nice because this is going to be a normal distribution. And they said 100, and my standard error was 2.4. So if we go ahead and hit the little plus, take a look at it. All right. So we can directly plug in is the 104.2 good or bad? Ooh, look at that. We come up with 0.04. That is my z-score. Okay? I didn't have to convert my z-score because on my table I didn't have to go from, a mean of 0. I could plug in directly what I had. So I'm going to get 0.04. So our z-score is equal to 0.04. All right, my friends. My friends, is 0.04 bigger or smaller than 0.01? Okay? So this is bigger than 0.01, which was the alpha. Okay? So this means we are going to fail to reject the null hypothesis and then didn't find strong evidence against the null. Okay? So let me ask you something, my friends. We're failing to reject. All right. Did the researcher shoot themselves in the foot saying that we had an alpha of 0.01? Okay? So we have to be very cautious about how we think about this. Okay? If I have an alpha of 0.01, that means I feel that there's a 1% chance that I'm going to make a type 1 error, meaning I reject the null when it's really true. Okay? So this researcher creating this was so confident that people that were left-handed had a higher IQ that, one, they didn't want to create a type 1 error. But in this case, because we're setting that alpha so low, I mean, if we set that alpha to 0.1, 0.1 means we have basically a 10% chance of making a type 1 error. Okay, but in this case, we set the alpha so low that we failed to reject the null. We didn't find strong evidence against the null in this case. Okay, so I guess in future, if you are doing statistics, if you're changing that alpha, the smaller that alpha gets, and the reality is the smaller you're trying to get to the parameter of what the actual situation is going to take place. Okay, so this would be like this itty bitty part of the normal curve. If we have the normal curve drawn up there, you know, like a 0.1 is like my two fingers here. If I made a 0.01, if I made a 0.1, it's a little bit fatter. Okay, so again, you're trying to find evidence away from it. I mean, I think that this is a pretty good study, and it's not showing that the lefties are have a higher IQ than the righties. What if I could do with both hands? You're cool. All right. You doing okay, friends? Everyone's all right? Yeah. All right. So does it all make sense, kind of, what my madness is going to do between today and Thursday next week? Yeah. So Monday quiz up till the 11th section of chapter 6 or 7, 6. So 6.8, 6.11, there should be a quiz. All rules apply. You could still work with each other on it. I won't be here. Hey, friends, do me a favor. Do me a favor. If you don't get done with the quiz on Monday, hand it into the sub regardless. Don't let the sub, oh, just take it with you. I'm not sure how dumb my last sub was going. Oh, you didn't get done, just take it with you. So, you know I'll take care of you. If when I see you on Tuesday morning saying, hey, a bunch of us didn't get done on the quiz, you know I'm going to do you guys right and give you the opportunity to do it in class. Just don't take it home. I mean, I don't know what the sub was thinking. I'm sorry. You know, it always amazes me when I come back and it's like, you know, I get a report that Claire was really bad in playing with matches. And it's like, Claire was playing with matches? Oh, that's pretty cool. I'm proud of her. I'm just kidding. Claire hasn't played with matches since 2019.
So if you want to turn this in?
Let's not turn that in because it'll be a good review because you'll have, I mean, theoretically, I could collect it right now and then give it back to you tomorrow. But I don't know. We've collected kind of a lot. Let's kind of chill. Hey, did anyone have any old homeworks that I need to be aware of?